Okay, so thanks for having me here. It has been quite an engaging week actually. So I thought that I will rather make a talk which is slightly lighter in mood. So we'll have a lot of videos and stuff, and let's see how much I can proceed with this. Okay, so resetting, there has been a lot of spat of experiments in developing theory and the experiments for resetting, which is some sort of a theory, a new development in statistical physics, and it has been slightly around a decade. And to enjoy this moment, Martin and Satya organized a meeting in Edinburgh where it all started a decade back. So we all gathered there to do something. Okay, and to discuss the new prospects, etc., etc. So it's like unlike the most of the topics here, it's the resetting is still at its infancy, so to speak. Okay, so the thing is, what I'm going to do, so I knew that this is not going to work, so I will just start again. So what we'll have here today is that I will try to slightly move away from theory, and so what you see on the left side is basically movement of animals, and this is a movement data repository where they actually record animal movements, etc. And you see that they actually animals locally move around. The birds basically they fly across continents. We'll try to see whether there are some sort of universal patterns to this, and to understand that, what we will do is we use something called an A-bot, which is an active robot, which you can make it in a lab, and try to see whether we can unravel some of these features that you see in the general sense in these foraging animal trajectories. Okay, so these two works were published in these two articles. If you interested in reading, you can take a look there. Okay, so some basic about resetting. So let's say that it's a very simple concept. So let's say that you are working on a research project and you get stuck. So what do you do? Like, you maybe take a break to think about it, like from a different perspective. So to speak, this is like a sort of resetting of your mindset that sometimes helps us. I mean, this is, I think, it's quite a thing that we have all done at one point of time. But what I like to say that this is not just simple qualitative anecdote, but there are also like real useful applications of resetting in different kind of systems which are interdisciplinary in nature. So what you have here is like a group of searchers, let's say, looking for some targets, and maybe once in a while, like they have to stop because of some reasons, and they have to renew their search. And so the point is, if you just keep on doing this thing, maybe you can gain some efficiency in search. And also in algorithms, so the algorithms essentially have different multiple pathways to find some sort of a specific target, but you can do timely restart in a way so it can actually do some efficiency, search efficiency. So another very interesting example is of this enzymatic reaction where an enzyme reversibly binds with a substrate to form some metastable state. And from this metastable state, what can happen is that either the substrate can be converted into a product, which would basically mark the completion of the process, or otherwise it can go back to the system so that the reaction has to start again. So one can actually show, as I speak now, that this unbinding process is almost analogous to restart process. So similarly, something that we have recently looking into is a problem which is very well known in the community, where you have an unfolded protein, and then the idea is that you have to go to the native state, which is basically, you can think about a very big rugged landscape. You have to go to the final, the minimum, the global minimum over there. But then what happens is the protein gets blocked in different kind of metastable state. These are called misfolded protein configurations, which basically are causes for Alzheimer's and stuff. So what happens is there is another type of proteins like chaperones, which come and facilitate this process. So essentially they come, and there is some sort of energetic process. It comes, drags that the protein from this misfolded state, takes it back to the unfolded state, and then where from the search for this native configuration begins again. So once in a while, all these things have some sort of general concept in nature, where you start from somewhere and then you are stuck somewhere, and then maybe you need to get out of that state to renew the process and find an alternative trajectories find alternatives so that you can actually weave through the detrimental paths. Okay, so I thought because it's a diverse community over here, so I thought maybe I will just show some very simple example how to realize a resetting process. So it's just a simple Newtonian particle. You start somewhere, there is a finish, and then just push it with a velocity v. Just you know, like it takes L by v, no stochasticity whatsoever. So now you can imagine the same process, but how to think about resetting. So let's say that you have your friend has an external clock, so it just basically tells you, okay, you know, like you are going at this point of time, just stop the process and take it back. So you just take it back to the initial position, and then you keep on doing the process till the particle eventually reaches this final position. So of course, in this case, if you can see, it's very intuitive to understand that, okay, this time will be always greater than L by V, because you're just stopping the process and letting it go back, right? It's very intuitive. But now imagine that you take this Newtonian particle and make it a thermal particle, let's say Brownian particle. So you immerse this, make this particle smaller in size and immerse in some water bath. So then what happens? So this is exactly the problem that Satya and Martin studied a decade back. So what they took is the same setup. So you have this Brownian particle which is diffusing in 1D. And then once in a while, with there is an external clock, what you do is just take the particle wherever it is and put it back again to the initial position. So this is a very simple exercise. This is what you do, and you stop the process when the Brownian particle eventually hits the target, right? So you have these two things. So there are two components of stochasticity. One is the diffusivity, and the second is the stochastic nature of time, the temporal stochasticity, right, which you are bringing. So what you can do is you can just take many samples, you can do an average, and then you can plot it as a function of this frequency at which you are resetting. So of course, if you do a plot like this, so surprising is basically this U-shaped plot shows that there is the global minimum, right? So there is an absolute minimum, and so it essentially tells you that of course there are many resetting rates which actually helps the process, but then there is also an optimal resetting rate which does the best. So I think this is the first observation that essentially initiated a series of works in this field, and we have seen many different progress. Okay, so the idea is this observation was not rather limited to diffusion per se, but you can actually think about general arbitrary stochastic process and also imagine how resetting can work over there. So just take this process, let's say look into this schematic. So you have, let's say, some stochastic dynamical process which is an ongoing process, let's say, and if it finds the target, you stop this. Otherwise what you do, like there is a resetting clock which comes and hits and tells you basically you have to restart the process, and from there you just keep on continuing the second part of it. So here I do not really specify what kind of process it is and where it actually resets to a particular location. It could be a configuration as well where you reset to a particular configuration. So the idea is here that you don't really need to look into the microscopic dynamics, what is going on here. What you can just simply look into the two different time scales in this problem. So one time scale is basically where the process itself hits the boundary. That's what I would call like some t, a first passage time, let's say, or otherwise it gets hindered by this resetting clock. So that's like when you bring the system back to its initial configuration or a set of initial configurations. So that's like a penalty that you do, and then after that the system renews. So it doesn't keep memory from the past dynamics. So that's why you see that this is an IID copy of this one. So this is a very simple stochastic renewal equation that you can write. The moment you write this, you can close this relation, and this gives you a simple, very simple formula. And if you note this formula, there is nothing specific about system or any other or even a resetting process, like what kind of clock you have, etc. Another thing I think which I should really emphasize here, this formula is also very useful if you are doing a numerics. Like for example, somebody who is trying to use it in an algorithm way, do not really have an understanding of what kind of stochastic process which is going on, then you can just play around with different time scales, right? You have two timetables, T and R, and then you can play around with this and still get this quantity which is the mean first passage time. So now the question is, for an arbitrary generic setup, so why does resetting help? And the question is, if resetting helps, when is there a finite optimal resetting rate? Is there always guarantee that you will see an optimal resetting rate? So this is something we try to understand for some time, and so I'm skipping the details. So what happens, So you can figure out that there is this quantity called coefficient of variation called CV, which is essentially a measure of statistical dispersion. It's a ratio of the standard deviation by the mean. Okay, so if this quantity essentially becomes greater than unity, so resetting is always guaranteed to help. But what is interesting about this particular result is that you look into this process, this quantity actually doesn't depend on the reset process. Okay, so if you want to add resetting to a process, and if you want to know whether resetting is going to be helpful or not, what you simply do, you just look into the underlying process, the reset free process, and look into this quantity. If it is finite and greater than 1, then it is guaranteed that resetting is going to be useful. So this is the way you can sort of like technical way or quantify the thing, like when there is when resetting is going to be useful, when there is an optimal resetting rate. But the point is, what does actually CV greater than 1 mean? So it essentially means that CV greater than 1 is basically a measure of how broad the distribution is, right? So if you think about it, so in the first problem, when the particle there was a Newtonian particle, right? The CV is essentially 0 because there are no fluctuations in this case, and resetting was not useful. So of course, this is basically this case where CV is close to 0. And then of course you can have also systems where CV is smaller than 1. And in all these cases, you can show that resetting is not going to be useful, and hence there is no optimal resetting rate. But this is the borderline, this is the marginal case, which is, let's say, for an exponential process or a Poisson process. But if you just cross this threshold and go to the other side, then it is always guaranteed that reset is going to be useful. And this being the case for the Brownian case, where CV is infinite. So this essentially tells us that depending on the distribution, the width of the distribution, resetting can be helpful. And this CV greater than 1 is not something new. It actually appears in many different contexts. For example, as I was telling you, the protein folding problem, this is a very classic problem where you have some sort of a dynamics which is going on in a multi-dimensional rugged landscape. You have many kinetic traps, etc., and then there are metastabilities. In these cases, because you get stuck here and there, CV is always greater than 1. But also you can have very simple situation where you have like two-state problem, like for example a chemical reaction with 2 branches, right? So here you have probabilities to go between these 2 branches with certain rate, etc. And here also you can show that depending on how much probability you can actually bias with whichever branch it is, here also you can create a CV which is greater than 1. These are some things which you can easily see in many different experiments as well as many theoretical results. Okay, so just to like summarize this part. So what we understood, that resetting can actually expedite completion of many different kind of stochastic processes, but it should not be taken for granted. There is a universal criteria. So if you follow that criteria, then you have a guarantee that resetting is going to be useful. And then there are also many other details. I'm not getting into that. Okay, so coming back to what I promised. So home range search process. So what is a home range search process? So many search processes usually, what you see around, are actually conducted in the vicinity of their favorite location, namely home. So for example, if you imagine that birds, they go out, right, and then they come back to their nests, right? Same as what the ants do, right? They also have nests. So for example, if you think about even mechanical machines, for example, drones, so they also go out but they have to come back to the docking station to recharge or refuel, right? So basically the home is something which is very important for any search process. And any search which is basically conducted around home, this is something which is known in the ecology as home range search process. So, and this is not something new, as Darwin himself mentioned almost 200 years back, that like it may be remarked that most animals and plants keep to their proper homes and do not necessarily wander about, and they always come back home. So this is what you see is a snapshot of bird trajectories, foraging birds. These birds are called sea gannets. So you find them in somewhere near the Scotland. So these birds essentially, there is a breeding ground. And so the birds go out and then they roam around for resources. It can be like food, it could be some breeding, etc. But then they come back to the same spot. So there is this home range search which basically keeps on going in many different setups. So the general understanding, if you think about it, a macroscopic view would be, so you have like, it's a cyclic process, right? You start from somewhere, you are looking for something, and then after some time you come back, right? You come back home and then you stay. So this is exactly captured by this schematic over here. So you search for something and then you return and then you stay at home. So this is, you can again try to write a same type of stochastic renewal equation, which allows you to get further insights into the problem. So the general questions that we had is like, can you actually say when home return is going to be beneficial? Because this is something very ubiquitous in nature. And second is this finite time resetting, because you see the initial examples that I had is that you were having like a Brownian particle or whatever it is, so you were just instantaneously reset it to the initial condition. But you see that in this case, any kind of animals or foraging entities will need certain time to actually go back home. So this is also can be understood if you are thinking about from an experimental perspective. So here what you see is basically a trajectory of a silica particle as a function of time. So it was sort of doing diffusion, but at some point of time when you had to reset, so what you do is just project the optical trap on this silica particle. You drag it all the way by using many optical traps to the center. Okay, so this essentially can take time, and so this is what is basically the avenue for So this is essentially the avenue for experimental setups as well that we have seen over the years. So as you can see here, so you just go here and then with certain traps, you can take it back in different ways. Like you can take it with constant velocity, something else, etc., etc. So what I would like to do is I won't go into this macroscopic view. I would rather focus on the microscopic view, in the sense that when I'm doing so what I was telling you here is that this is a general macroscopic view where you search, you return, etc., right? But the question is, how do you actually return? Can I delve into the microscopics into this homing mechanism? That is the thing which I would like to understand. So actually this is a very fascinating phenomena if you have noticed before. So for example, let's say just simple ants. So simple ants, if you have like some sort of a very sparse food distributions or something like that, so what they do is they usually use pheromone trails, right? We all know, I think, pheromone trails. So they just basically follow it, and then that's how they also come back. So there is a concept of path integration which is being used there. But Saharan desert ants essentially cannot actually do that because of the surface temperature, because the pheromones essentially evaporate. So what they have to rely upon is something called olfactory cues or odor films. So in this case, what happens is like they have some sort of a odor landscape and then try to navigate through this odor landscape. And that is how the desert ants, they actually come back to their nest. And it's, of course, there's just not only one nest, they can also have multiple nests because it's a very, very vulnerable environment. So another very interesting creature is this something called dung beetle. So what dung beetle essentially does that, so it has to collect, the beetle actually has to collect some dung, and it has to take from one place to another place. Okay, this is essentially the process. But then what does it do when it tries to take it? So what it does, I don't really have a video. I was trying to put it, but it didn't work. So it basically pushes the dung through his rear legs. So once in a while, what they do is basically they go on top of the dung. Okay, they go on top of the dung, and then there are some sort of a celestial cues. For example, let's say Milky Ways, etc., direction or direction of the wind, etc. So and then they basically reorient themselves. Okay, so they reorient themselves just sitting on top of the dung, and then again come back, and then they have a new direction, and they basically push the dung along that way. Okay, so this is something I would be focusing on. So this is something which we call reorientations, right? Reorientations or course corrections. So there will be many such instances. The list is very long actually, and you can see similar pattern also in homing pigeons. So the point is, can you understand these universal patterns in homing paths using some robust system? So we were interested in this, and then a friend or colleague of mine from IIT Bombay. So he was designing something called like a light controlled robot. So this is actually a very simple robot. So if you can think about this is the size of the robot. So around like 1/3 of a kilogram. what it has is basically it has a couple of sensors. Okay, it has infrared sensor and it has light intensity sensors. So light intensity sensors, what they do is basically emit lights, and then it can sense something which is in front of it. And it has also wheels, so you can see the wheels over here. So there are these wheels, and these wheels basically are controlled by us, in the sense like from outside you can basically program these wheels, so the wheels will have their own dynamics. Okay, so this is the top view of the robot. So what it can look for, the way this robot is supposed to function is as follows. So it will basically look for some targets or payloads that we will design in some sort of an environment. So once it finds this payload, it has to come back. It has to come back to something called a home, which I will also show you. And the point is, what kind of dynamics this robot can perform. So we have shown that this robot actually can perform a plethora of dynamical systems. This is simply because we have full control over this dynamics of the wheels. And then of course, as I was telling, that any kind of obstacle comes, or when it has to find the target, it basically finds this via some sensors. Okay, so let me just show you like how you can, it's just benchmarking some of the things. So this is the robot you see. So it can, what I'm trying to show here, it actually can perform Brownian motion to run and tumble particle, active Brownian motion, and all the way to Levy works and things like that. Okay, so here you can see the different trajectories, and all these things usually being done by feeding appropriate dynamics to the wheels. Okay, so just how to engineer this robot is very simple. So you have, this is a Newtonian robot, right? This is like something which you can see, it has like, it's 1/3 of a kilogram. So it has these wheels, right? So it has a certain velocity VL and VR. So you can write usually this kind of dynamics, right? For this one, this is a Newtonian dynamics. So nothing fancy, I mean nothing stochastic in this part. But now what you do is this VL and VR, they are actually the velocity of these wheels, you actually put some stochasticity over there. Okay, and I'm just for this active Brownian case, I'm showing how to do that. You can do a systematic way. You can add this randomness in this case, and when you do this essentially becomes more like active Brownian dynamics, which we have seen many times in our in this conference. So, and the effective diffusivity in this case, of course, will depend on how you choose the noise and after what time. So there is a certain delay time, right? Because nothing is instantaneous, it's a real process. So after every epsilon second, you choose a random variable and feed it to the wheel. So it essentially depends also on epsilon on that delay time. Okay, so this is the way actually the foraging happens, right? So you see that this is the robot, this is a home. So what you are seeing is basically a circular arena. H over here is basically the home, and there is a light intensity. So light intensity is maximum actually at this home. Okay, and now what the robot does, so let me just play this video one more time. So what the robot does, essentially it goes out, right? It is performing active Brownian motion. So and then the periphery of this arena essentially is reflective. So it just goes to the periphery and then reflects back, and so it basically keep on doing that till it finds the target. Okay, so this target is basically what you see here. So it has something called flanks, the robots, and then whenever it sees the payload, it can actually attach to it. So it cannot be unlocked. So, and this is the way it brings it back. So let me again show you this video. So it's just doing this foraging behavior, right? So it's a foraging movement, it's active Brownian motion. And then you will see that at a certain point of time, that's it, bingo, and then it brings it all the way back to home, right? So what you see, what are these arrows, right? So what are these arrows? So these arrows are something which I have been telling you. This is what we are calling course corrections or reorientations, okay? So how does it do? How does the robot actually know that when to do this reorientation or course correction, right? So it's actually very simple. See, at any point of time, because this is an active Brownian motion, performing like an active Brownian motion, see, will have certain direction, right? So let's say this is, I am a robot, and this is my home. I know I have a home, there is a home over there, and the home has the highest intensity of light, right? So at every point of time, at every instant of time, I have light intensity once in my front wheels and also in my back wheels, okay, on my rear wheels. So I keep on measuring the difference between these intensities, Okay, this is something we can do in experiments. We can measure. So if you just focus on this one, the third panel over here, so you can see that if IF is greater than IB, which essentially means that the front intensity, front wheel intensity is actually higher than the back wheel intensity, the robot doesn't feel anything, it is coming towards the home very well, okay. But the moment this IF essentially becomes less than IB, so then this is actually the case where robot is slightly drifting away from the target, which is basically the home. So this is exactly the condition we put it in the system, and when this happens, yeah, okay, how much time? 10 minutes?
No, so now time.
Oh, is it?
Take a couple of minutes.
Okay, fine. Okay, so when this happens, so essentially this is the time exactly the robot knows that, you know, like I have to reorient, okay. And these are the angles, this is basically the small arrows which you see over here, essentially mimic the reorientation events. So how to understand this via the lens of stochastic resetting? You see that in this case, we are not really resetting the particle's position, okay, which basically most of us are used to seeing, right? You have like X and Y, you see that I am bringing the particle back to the origin, etc. But what is happening here, if you think about it, this is the robot. So robot has certain direction, and let's say this is theta, which is everybody knows. But what is interesting here is there is also another angle we can construct, which is basically the angle between the robot's instantaneous direction and the direction towards the home, okay. So this is basically the phi. So what is happening is that if you look into the dynamics of phi, so that is actually being reset. So here you have an effective orientational resetting, but not just a simple theta orientational resetting, but an angle which is basically the instantaneous difference between the instantaneous direction and the angle towards the home. So this is something you have. So what you can do is that from simple active Brownian dynamics, you can try to write an effective equation for phi, and then you can actually apply the resetting dynamics to the phi, okay. And then once you do this, you can derive some results, etc. So I'm not getting into the details, so because I don't really have time. So what we are trying to do is that in experiments we were trying to look into the time it takes, basically the homing time, right? The homing time that we were after, and dr is basically the rotational diffusion constant that we can actually tweak from outside. And what we saw is that as you keep on increasing, it first linearly increases, and then after some time it saturates, okay. So this is something we saw it in experiments, and we did the theory and the simulations via resetting, and we also saw the similar behavior, okay. So then we sort of like what we conclude from here is that there is a insensitivity to dr after certain threshold, okay. So it essentially means that there is an enhanced homing efficiency after some time. So for real systems, this would probably mean that the robot, the foraging entities, etc., probably have learned after some time how to behave in a more efficient way. But for the robots, I think the way we understand this, very near to the home, you have very high intensity. So as fast as you can reach towards the home, after that it doesn't really matter. So the effective idea is to come close to the home as soon as possible. So this is what I really wanted to, what I meant essentially, that if you have a critical diffusion constant which is smaller than this dr star, after which it saturates, so then it's more persistent, of course, and it comes over here. But you see that for this case, it's basically noisy in short times, but then once it comes closer to the origin, after that you see that the homing time essentially becomes indifferent. Okay, so I think I will not take much of your time, and I just wanted to basically just finish with this slide, that we also try to test our theory with this experiments which was done using these homing pigeons. So in Oxford nearby somewhere. So what they were doing is that they were releasing birds in a group of 2, 4, 8, etc. And so essentially what it means that if there are, so of course they say that this motion essentially can be said as a correlated Brownian works, but there was no concrete theory there as well. We are not also claiming any concrete theory for it, but we are just trying to understand whether there is some sort of a pattern between these two systems. So what you can understand that if there is one guy which is flying by itself, So then of course it will make a lot of mistakes, right? Because there is nobody to guide. But if you are flying in a flock of 8, then there are more guidance, right? Because they are probably interacting with each other locally, and then of course there is some correlation factor you can calculate. This is essentially what we also see from our robot experiment. Okay, so I think I have really superseded my time, so we'll just stop here. So I think we have some sort of a controlled system which can mimic many different kind of behavior, like especially foraging and homing behavior. There is some sort of an optimality that we see here. We are sort of trying to understand it even better. So I think I need to put, so there is this, I have to acknowledge these guys. So these are these two very bright PhD students. He is Somnath, who is doing the experiments. Arup, who did the theory, he's from Math Science. So Harsh is a colleague and from IIT Mandi. Nitin is a long-time friend and a colleague also from IIT Bombay. If you're interested, these are the articles where these works were published. And so thank you very much.
Long live India and France friendship.